Hello ECA students! This week we will continue our solutions unit by looking at acids and bases. Please note that you can pause the video to take notes or to take a break at any time. For assignments this week, just like last week, you will have a quiz based off this slideshow, a lab with analysis questions, and a reading with a response. This week is also worth 50 points. In this slideshow, we will look at properties, characteristics, and examples of acids and bases. We will define acids and bases as solutions, building on what we learned last week. We will also learn about pH, neutralization, and pH calculations. Let's get started. Acids. We have heard this word many times in our life, and we're pretty familiar with acids. Acids tend to have a sour taste and occur naturally in many of our favorite foods. Acids are delicious, if you ask me. They are tangy, tart, and sour. Acids have the ability to produce H+ ions, hydrogen ions, when in an aqueous solution. We remember that word from last week. A solution where the solvent is water. Acids have a pH between 0 and 6.99999, etc., where 7 is a neutral pH, like water. We will learn more about that in a minute. When in a solution, acids not only produce a cation of hydrogen, they also produce an anion too. Acids have the ability to break down certain metals and are in a few cleaning products. Some common acids are hydrochloric acid, which is stomach acid, sulfuric acid, which is battery acid, nitric acid, and acetic acid, more commonly known as vinegar. Bases. We may have heard of bases, but we have a hard time identifying them sometimes. Strong bases are actually pretty harmful to most living creatures, which is why they make great cleaning products to keep bad germs away. Bases tend to be slippery or soapy to the touch. When fatty substances like grease interact with bases, they dissolve. Most soaps are basic because of this ability. We talked about the soap molecule last week, and we will talk about it again this week. Soap is great stuff. When in a solution, bases will accept hydrogen ions in water to create hydroxide ions, as you can see, OH-. Bases tend to be bitter or chalky. However, most foods tend to be acidic. The most basic food you generally would eat would probably be an egg, which has a pH of 8. Bases produce a negative ion of OH-, a hydroxide ion, but produce a positive ion too, usually an alkaline metal. Bases can also corrode metals. Examples of bases include sodium hydroxide, commonly known as lye, which can be used to make soap when combined with a fat. Potassium hydroxide, which used to be called caustic potash, and which is used in detergents and as a common fertilizer. Magnesium hydroxide has been called milk of magnesia in the past and is used as an antacid as well as a laxative. Ammonia is a weak base that is used as a cleaning product and as a fertilizer. A way to identify some, but not all bases, is to look at the periodic table. In the previous slide, we had examples of sodium hydroxide, potassium hydroxide, and magnesium hydroxide. Each of these examples ends in hydroxide, so there's a hint that if it has a hydroxide ion, it might be a base, but this isn't always true. The OH- can be paired with a positively charged metal. If we look at columns 1 and 2, right here and right here, we can see that they are named alkali, or alkaline earth metals. Alkaline is another word for being basic. In those columns, we can find the sodium, which is right here, the potassium right here, and the magnesium metals. So if we combine a hydroxide with an alkali metal, we may very well have a basic compound. This trick will not help you identify all bases, but it will help you identify a few. All right, so let's do some practicing of identifying acids and bases. In our first equation here, let's see, we have HF and BaOH2. We can use our hint we just learned to note that Ba here, barium, is an alkaline earth metal, and the compound contains an OH, or hydroxide here. I think we can safely assume that this is the base. We look at HF here. When separated into ions, we have a free H, or hydrogen ion, which will actually combine with water to make H3O+, which is a hydronium ion. And then we'll have a free cation, this will actually be a free anion of fluorine, which is a halogen. Another trick, let's go back to our periodic table. We can look at our halogens, our halogen row here. If we combine a halogen with hydrogen, we very well might have an acid. So we can identify HF as an acidic compound. Right here. All right, so there's our base, there's our acid. Let's look at the next one. We have HCl. H is a hydrogen, Cl, chlorine, is a halogen. We can safely assume that that is our acid. We know that is hydrochloric acid, which is a stomach acid. And then here we have NH4 and OH. Since this is our acid, we could probably safely assume that this is our base because it has that hydroxide. But if you note in this case, it doesn't have that alkaline metal. However, this can still be a base. That's why the trick doesn't always work. So out of process of elimination, here's our acid and here's our base. That should help you with the quiz. All right. Acids and bases are solutes in aqueous solution most of the time. The acid and base ionize, we remember that word, into charged particles and become electrolytes. That's another word from last week. The solution is able to conduct electricity. Pretty cool. An old-fashioned liquid battery would use battery acid, which is actually very, very dangerous. The anode and cathode would allow for the electrolyte to create an electric current through the circuit, letting our light bulb shine. I think that's pretty cool. The important vocabulary words are hydronium ions and hydroxide ions. We just talked about those a minute ago. Hydronium ions are water molecules with an extra hydrogen and a positive charge. The more acidic a solution, the higher the concentration, there's another word from last week, of hydronium ions. Hydroxide ions are an OH ion with a negative charge. The more basic a solution, the higher the concentration of hydroxide ions. All right. So pH. pH stands for power of hydrogen or power of hydronium ions. The pH scale runs from 0 to 14. A pH of 0 would be a very strong acid. pH of 7 would be a neutral substance like salt or pure water. A pH of 14 would be a very, very strong base. So a pH of 0 would have a lot of hydronium ions. A pH of 14 would have very, very few hydronium ions, but have a lot of OH minus hydroxide ions. You see here, hydrogen ions, very, very small amount, very, very large amount of OH ions. Here we have a very large amount of hydrogen ions. We have a very small amount of hydroxide ions. pH is a measuring system that measures the concentration of hydronium ions. The term power means to what power or exponent the number of hydrogens is. We will use logarithms to determine this. If logarithms are too confusing, don't worry too much. Just find the logarithm button on your calculator, and that should be what you need for the quiz. The way pH is measured is in molarity. We find the concentration of hydronium ions in a solution in moles per liter. This number is usually a small decimal. For pH of 7, we have a molarity concentration of hydronium ions that is 0.00000001 molarity. That's a pretty small number. If we put that in scientific notation, we would have 1 times 10 to the negative 7 molarity. The 7 comes from the exponent, or power here. And that 7 is our power of hydroniums. The pH scale is logarithmic, and the smaller the number, the greater the concentration of hydronium ions. Kind of backwards if you don't know about the logarithmic function, but once you do it, it clicks. If a solution has a pH of 1, that means the concentration is 0.1 molarity of hydroniums. If the solution has a pH of 2, that means the concentration of hydronium ions is 0.01 molarity. A pH of 1 is 10 times greater than a pH of 2. A pH of 8 has a concentration of hydronium ions that is 100 times less than a solution with a pH of 6 due to the decimal point location of the molarity. Essentially, the smaller the number, the higher the pH. If we go from 0 to 14, each pH is 10 times greater than the number after it. The greater the concentration of H3O plus hydronium ions, the greater the acidity and the lower the pH. The smaller the concentration of hydronium ions means that there is conversely a greater number of hydroxide ions. With small concentrations of hydronium ions, the pH is higher. Equal amounts of hydronium ions and hydroxide ions are neutralized by each other, and the pH is 7. This is probably getting repetitive at this point, but it's actually pretty easy to get these mixed up. So a strong acid is an acid that has a high solubility and completely ionizes all the compounds. A weak acid has a lower solubility and can only ionize or dissolve a few compounds. Being a weak acid does not mean that the acid is not dangerous. Let's think examples of strong and weak acids. Strong acid would be stomach acid, HCl, which has the H and Cl ions almost completely ionized. A weak acid, like vinegar, only has a small percent of ions dissolved because the molecule has strong bonds due to the elements that make up the molecule. But concentrated vinegar is still very dangerous. The really cool thing about acids and bases is that when they combine, they neutralize, meaning the pH becomes closer to 7 in the middle. This would be handy when trying to control pH. Salts and water are products of neutralization, and both have neutral pHs. The reaction is a double replacement reaction where the hydrogen and the chloride switch dance partners on the product side. The products are life-giving water and delicious salt. Toothpaste has many uses, but the main one is to neutralize the acidic compounds in our mouth. We have lots of bacteria in our mouth, and they go through anaerobic respiration after they eat the leftover carbs in our mouth. Kind of gross. When we don't have enough oxygen, we go through anaerobic respiration too. That's what makes us sore, because we produce lactic acid. The acid can corrode or break down our pearly white teeth. Toothpaste tends to be very slightly basic and sometimes contains basic ingredients like baking soda. Basic toothpaste will neutralize the lactic acid so it doesn't break down our teeth. Pretty nice. In your quiz, you will need to calculate pH. Don't worry, it's not too bad. Alright, I'm running out of time on this video, so I'll make a short second video to do the calculations. Alright, see you in a minute.